And most often when we want to do our simplifications, we have to resort to the use of integers. Ike, your video is on. I know you have handsome face, but me too, I wish I can show my face. Should I show my face?
I'm sorry, sir. I'm sorry. Forgive me.
If any of you show your face again, me too, I'll show mine. You can't be cheating me. Hello, fam. Hello. No class.
Everyone said we can't hear you.
Yeah. You can't hear me. It's true. Something was holding my neck.
So are you safe?
No, I had a call from a big man. I cannot,
Yes.
but I should have excused you. Sorry. Okay, so these are
you
that
safe?
is. Oh, we are safe. I'm safe. You are safe. Okay. So I think we were here, so we can move from there. So now we come to. So can we go online and then look for the meaning of integers? Integers. What are integers? Can we do that? What are integers?
Hello, sir.
Yes. Oh, please, we have 2 minutes to do that. Let your colleagues also information. Let your colleagues also
and negative whole numbers.
And you have 5 minutes to discuss that, and I'll let what's his name? Oh, the gentleman who led this morning's own, Foster. Am I right? Or is one here? Is Foster here? Foster is one here.
Please, I'm here, please.
Yeah, Foster. Let's give your colleagues some 3 minutes for them to go online and look for the definition of integers and with examples. Then when they come back, you give them another 3 minutes for you brainstorming with them. Then you quickly hand over to me.
Okay, thank you.
Okay.
Then we can talk about this. Okay, you can start with them.
Okay.
Since they said they are
My hand
ready.
is up. My hand is up.
Your
Yes,
hand is
let's-
up and we can't see you. Are you Regina? Are you Regina?
No,
Oh,
I'm,
you
I'm
are.
Isaac Mensah.
You didn't raise your hand.
Isaac Mensah.
If you raise your hand,
Isaac.
it will show here. It will show. I can see William. William has raised his hand. You haven't raised your hand. Isaac, you have not raised your hand.
Isaac, my hand is up.
Yes, Williams hand. Yeah, Williams, let's hear from you. Hello?
Please, can I say
Oh.
my own?
Okay, you see
Yes,
it.
you can.
Yeah, check.
Yeah,
Take out.
Okay, Mr. Forster, can
Yes.
you hear me?
Yes, I can hear you.
Yeah. Yes, I would say integers are positive and negative whole numbers.
Okay. Give us one example.
Yeah. One, negative 3. Then 1, 2, 3 are all integers because it is combination of positive and negative whole numbers.
Okay, bro. 0 is part 2.
Yeah, I was about to ask the question.
0 is also integer, so you can't forget the 0.
Yeah, he's asking whether 0
All right.
is an integer.
Yes, 0 is an integer.
Yes,
Yeah,
it's an integer.
Good. Because do you have reason for that? Can you give us reason why you think 0 is an integer?
Yes.
I think 0 is a whole number. Yeah, 0 is a whole number.
0 is also a number, but yes,
It's a whole number. That's all.
yes.
Good. Yes, because
So it's also a number.
okay. There's someone up. Hand is up. Let's hear from Stephen. Stephen. Hello. Okay. Hamza, let's hear from you.
Okay. An integer is a collection of positive and then negative whole numbers, a set of positive and then negative whole numbers. Yeah.
Yes, positive.
Which is 0 2 is a positive whole number. Yeah.
Okay, so let's can we have some properties of integers?
Okay.
There's some basic properties of integers.
Right. Yeah.
Okay, can you hear me? Hello? Is someone hand is up?
Yes, please.
Okay, we have Eric here. Let's hear from you. One property.
Okay, so a property of integers, as we were made to understand, those also they are denoted by the letter Z. So once you see the letter Z, you can know this particular or set of numbers is talking about integers. So they are denoted by the letter Z. Capital.
Please, what's the meaning of the Z?
That's the symbol used to represent the
Symbol to
in terms of
represent
the
integers.
numbers.
Symbol.
But there should be a meaning to it.
It's a symbol we use.
Yeah, my understanding to the Z is that the Z is German word, and it is called Zalem.
Alright.
So if a German says Zalem, means positive and negative whole numbers, that which is what the integers.
Yes.
So the Z meaning Zalem in German word. That's ZAHLGM. Zalem.
So I think it's louder. It's loud, but it's all boiled to the same thing. Thank you for the update. So first,
Okay, let's also hear from Stephen O2. Give us one properties of an integer.
Yeah, what I know is the closure property,
Good.
which says that under addition and subtraction, that's the
Yes.
addition of two numbers or the difference of two numbers will always give an integer.
Good.
Yeah. Okay, so please, with that, do you have any example for it when it comes to?
Yes. Yeah. So Eric, Stephen, let's hear from you if you have an example.
Okay, let's say m and n represents two integers. So m plus n will give you integer, and then x what they call it, m minus n also give you an integer. Example, let's say the m represent 3 and then the n represent 2. So 3 plus 2 give us 5, which is an integer, and then 3 minus 2 give us 1, which is also an integer.
Okay,
So
let's also hear from
Mr. Foster, I have a question.
yes, you can ask. Go ahead and ask.
Yeah, please. I just want to know if the integers can be denoted with any letter.
Yes, you can do that, but you will have to define it.
Okay.
Please, I don't think so.
There's something I want to add.
Yeah, it should be Z. It should be Z, and that's it.
So apart from that, we cannot denote it with any letter. Is that so?
Yeah.
Because if you take the real number system, we have rational and irrational numbers. They all have their unique letters. And under rational number, we have the integer, whole numbers, and natural numbers. See, they all have their unique letters.
Okay.
Yeah, that is it. That is it.
Yeah.
Okay, so please,
very important I want to add. Let me add something.
Chair, hurry up and
John, my hand is
ready.
up. My hand is
Okay,
up.
so-
John, my hand is up. My hand is up.
John, you didn't indicate your hand is not up. Those hands, we have Michael, we have Eric. So John, I can't see your hand. You need to indicate that.
Okay.
But let me contribute this. Let me say something. I want to add something to what you are saying.
Yeah, even though your hand is not up, but you can contribute. Yes, let's hear from you.
Yeah, what I'm saying is that integers are numbers that can be positive or negative or zero, but can never be a fraction. That cannot be a fraction. So please, let's take note of that.
Okay.
Let's take note of that. Cannot be a fraction.
Okay, so let's just summarize what we've seen. What our colleagues have just contributed. We are saying that integers are positive and negative whole numbers. That is why 0 is inclusive. We cannot say integers are positive and negative natural numbers, because if you are saying natural number, 0 is not a natural number. So we are saying that integers are positive and negative whole numbers denoted by alphabet Z. And we are saying that we have properties of integers. We have closure properties. We also have commutative properties. Yes. We have the associative and we have the distributive. All these are the factors that contribute to the properties of what? Integers. And so we are saying that when we talk of, my friend already explained the closure property. When we talk about the commutative property, we are saying that if I'm using x plus z, x plus y, it should be equal to what? Y plus x. And that is so. If you are going to use the letter to represent numbers, that means that if I have 3 plus 5, which gives me 8, the same 5 plus 3 should also give me 8. That is one property of what? Integer. Another property that we know is associative property. And so we are saying that, let's say if we have x plus everything in brackets, x plus y should be equals to what? X plus y, everything in brackets plus z. And so if we expand everything, at the end of the day, we are going to have the same number. So we also have the distributive property, which we all know. But we have to also bear in mind that in the case of distributive property, one thing we know is that when you are using negative numbers and that of positive numbers, if k is not there, at the end of the day, you are not going to have the same result. But if you are using negative numbers in the case of commutative property, both negative and positive numbers, in the case of commutative property, you end up having the same result. In a nutshell, what we are just trying to say is that integers are positive and negative whole numbers, and these are the properties, and they are discussed into detail. We have the closure property, we have the commutative property, we have the associative, and we have the distributive property. So these are the property, and as well as the identity property. So these are the properties that is associated to what? Integers. And our lecture will come in and give us details into the various properties that we have. And so one thing we must know that 0 as a number is an integer. And that is why we are saying that integers are negative and positive whole numbers. So
I can never be a person. I cannot be a person.
Pardon?
I cannot be a person.
Yes.
No.
No. We are saying that, look at it. That is what we are saying, that fraction is part of a whole number. I don't know whether you are getting me.
No, fraction is not part of whole number.
I'm coming.
Fraction
Let me
is
explain. I'm coming. Let me come this. We have proper and improper fraction. Let me explain.
Fraction is a rational number, but it's not a whole number.
I'll allow you to come in. Let's say we are talking of proper fraction, whereby the numerator is smaller than the denominator. Let's say I have 1 out of 2, and 1 out of 2. Can we say it is a whole number? Like, let's just share ideas.
Please, where we are going is different from. It means we are deviating from the.
Yeah.
We are
So if someone has anything, no, if someone is having any idea, the person can come in. I mean, we are teaching ourselves.
So please, I think. Hello.
Yes.
Hello. Yes, please. So I think yours has to do with semantics.
Let's allow one person to talk at a time. Yes.
Mr. Foster, you should point.
Yes,
I've come in.
We are not allowing the flow. Let's one person talk at a time, please.
Yeah.
Yes.
Please. I've come. And please note this again. Hello, can you hear me?
Yes, we can hear you, sir.
Please, you people should note this. You see, once there's a chair, and even apart from the chair, I have my TA also here. Once there's a chair and the chair is in charge, if I'm not around, my TA is there. If the chair was presenting and maybe my TA decided to allow the person to continue with the chairing, that is fine. But please, let's respect the chair. Okay? You cannot be talking. Let's respect it. This is an academic platform. And don't be doing things that your students will be doing, that you complain about them. When you do that and you come for the face-to-face, I'll come there with a K. That's just by the way. Okay.
Please don't say that. Don't say that, please.
Yeah, that's just by the way. So please, let's respect the chair. It's not easy chairing. Okay, so I have listened to all that you have said, and you have made the whole work easier for me. Your definition of integers was good. You said positive and negative whole numbers, including 0. Okay. Or you said positive and negative whole number. Is that not what you said?
Yes.
And whole. Okay, fine. That's fine. So, and when it comes to the commutative property, I heard one of your colleagues say that when you have x plus y and it's the same as y plus x, then that is a commutative property. This one, you were very excellent by saying that we are discussing the properties of integers. So you say that if x and y are integers, if x and y are any two integers, okay, then x plus y will be equals to y plus what?
X.
So say it that way, because you are talking about properties of integers. But all that you said they were perfect. Okay. So we must also note that I think you talk about the closure property, and it was also there. The distributive property. Remember, multiplication is distributive over addition.
Addition, yes.
But not the other way around. Distributive over multiplication. Whether addition is.
Yes.
You see that it may not work in all cases unless.
Yes.
Will it work in all
cases?
No,
it will not work. That is why I said when in a case where there are negative numbers involved, it will never work in all cases. So I made it clear on that.
Okay. And this is a generalization. That's why we are saying for multiplication it is distributive over what?
Yes.
Addition. Then when we come to distributive, note that two operations are involved.
Yes.
But when it comes to commutative and associative property, only one operation is involved.
Yes.
But associative, three integers are involved. However, with one, one operation. Then when we come to, excuse me, let me pick. Hello. Yes, sir.
Hello, sir. We are listening.
Yes, excuse me. I'll get back to you.
Okay, thank you.
I'm trying to let me come.
Okay, so please, I want to ask this question.
Yes, you can go ahead.
Okay. So, looking at the commutative property.
Yes.
The operation on commutative property, does it work for all the 4 basic operations? Let's say, does it work for the multiplication, division, addition, or subtraction, or it has specific operations?
No. It doesn't work for other 2 of them. It only works for multiplication and addition. For division and subtraction, it doesn't work there. Example is if you're having maybe 4 minus 2 at the right hand side of an operation, and the other side is going to be 2 minus 4. One side will be positive 2, the other side is going to be negative, I think 2 or so. Yeah, so it is only the multiplication and addition that it works for. So we say commutative and associative are both addition and multiplication are both commutative and associative. So it works for the 2.
What of the associative property?
It also works there. Addition and multiplication works for associative as well.
Yes.
Yeah, but it doesn't work for the other 2 operations.
There's this question that I made, of which they were demanding which of the following are closed under associative properties of integer. So they list them, this, and then all the four were listed, and then they started I and I and I. That's why
Okay.
I need to
Okay. So
calculate.
probably it's going to be the two, but not the other
No.
two. Uh-huh.
Okay.
Okay.
Then
Please,
what of
is
the
the screen on? I can't see it from my side.
I think the screen is not on. Maybe
All
probably
right.
Prof has done something to it.
Okay.
okay? So I'm going to say so with the four basic operations under the distributive property, which among them or does it work for all?
Please come again.
Yeah. The question is not that clear.
Okay, I am back. Now, what is happening?
So ask your question again.
Uh-huh.
We are listening.
Does all the four operations work for the distributive property?
No.
We
It
didn't
doesn't
say
work there.
for all the operations. We said addition and multiplication.
Yes, that is all.
Say no. My question is on the distributive property.
Uh-huh.
Yes.
Yeah, the distributive property. That's what I'm asking.
No. Still, it doesn't work there. I think over there too, still, you are going to use the addition and the multiplication. Because in as much as for the distributive property, if you are maybe adding, multiplying 2 by the bracket, maybe 4 plus 2, it wouldn't be the same as multiplying 2 by 4 minus 2 in the same bracket. So I think for all the four operations, properties, the operations that work on it is maybe the addition and then multiplication. Division and multiplication, the subtraction doesn't work anywhere. I stand to be corrected. That is my point of view.
Okay. But I like
Okay.
Okay, profit. Okay, profit.
Yeah, I think there is no call for alarm. You need to revise your the how do you call it, your real number system, and follow it up with the operations or the performing some of these operations and looking at these properties, associative, identity, distributive, and then the commutative property. We mentioned that for the distributive property, usually it is one operation that is distributing over the other operation. So it means there will be two operations involved, but one operation will be distributed over the other. And we are saying that for the investigations we have done, we have explored the real numbers. The investigation we have done, it is multiplication that is distributive, always distributive over what? Addition. So we are trying to say that if you have 2 into brackets 4 plus 5, it is the same as 2 times 4 plus 2 times 5. This is what we are saying.
Yes.
But turn it the other way and have it as 2 plus into brackets 4 times 5, and try it and do it 2 plus 4 times 2 plus 5, and see whether 2 plus into brackets 4 times 5 will give you the same as 2 plus 4 times 2 plus 5. Will it give you the same?
No, please.
It will not.
So that's why we are saying that the first one you will get 22, but the second one you get 8 times 7. You get 8 times 7, which is more than the 22, right? Hey. So that tells you that addition is not distributive over what? Multiplication. You can investigate that further, okay? Now, the identity property. The identity property too, I think you talk about it. We have identity property for addition and then multiplication. So the identity property is that element that when you add it to a certain number, it gives you the number back.
That is it.
Or when you multiply it by a certain number, it gives you the number back. So we are saying that 0 is the only additive identity that when you add it to any number, it gives you the number back. And when we come to multiplication, we said 1 is the multiplicative identity. I hope that is fine.
Please take it again.
Hello. Hello.
Yes, yes.
Yeah, so maybe what I can also add is they're also saying that -1, 2 is only number. When you multiply by any number, it will give a negative of that value. And that one too is also part of.
And we have inverse element.
Yes.
We have inverse element. Okay, so I think we have some of the examples here. When we pick the addition, 4 minus 5 is the same as 4 plus -5, and that is under how do you call it? I think commutative property. So 4 minus 5 is the same because that 4 minus 5 is the same as 4 plus -5. And it will be the same as -5 plus 4. You get -1. When we come to
slide, you cannot do that.
That's for closure.
That's for the closure.
Yes, please.
Okay, the first one is for the closure.
Well, please, we can't see your screen now.
You can't see my screen.
Yes, please.
Can't you see it?
No.
No, please.
No, please.
The screen is not coming.
Because the network took us away.
And we can see.
So here we have the closure property. And the closure property states that when you add, subtract, or multiply any two integers, the result is always an integer. So the result belonging to an integer is what makes it a closure. So it is closed under integers. Whether if you add, subtract, or multiply any two integers, the result that you get will still be an integer or will still belong to a set of integers. That makes it a closure. That makes it to be closed under. That makes these operations to be closed under, how do you call it? Integers. Hey, is that right? Or integers to be.
Hello. Yes.
Yeah, it will be closed under integers.
Okay, so
for only integers.
Okay, so these operations are closed under integers, right? Because when you add or subtract any two integers, the result will always be an integer. So that is correct. Okay.
I want to ask a question about the integers and the real numbers. So what are the difference? So this particular number belongs to integer or integers, and this also belongs to real numbers. So I want to know the differences. Is it because when a number is irrational number, we don't put it under real number?
So we have when you visit the real number system, we have rational and irrational numbers. So both rational and irrational numbers all belong to real number system, or they are real numbers. Okay. Okay. Right. So the real number system consists of rational and irrational numbers.
Okay, that is integers. Hello.
The rational numbers can be considered. Oh, what are you saying now?
Prof.
Yes.
Please, I want to contribute based on what my friend is asking. If I can, I give him some small discount.
Okay.
Yes, you can go. Yes, you can go ahead.
Okay, so please, when it comes to the real number system, I think that is the universal set. Then we have the rational and then the irrational numbers being the subset under the real numbers. So under the real numbers, so under the rational numbers, we have integers being subsets, and then whole numbers also being what subsets under the rational numbers. So all these examples that we are saying as integers, they are all subsets of the real numbers.
Okay.
So I think that is clear, right?
Yes, please.
Then the closure property too, we have examples, and you have given examples even already. So that's one when you add two numbers, irrespective of their position. If the first number is added to the second number and we decide to turn it where the second number is now the first number, and we are adding the first number to, you get the same result. So for instance, if you have 6 plus negative 8, is the same as negative 8 plus 6, right? But when we look at division, division is not commutative. It doesn't work for division, and also doesn't work for subtraction, right? Because 4 minus 6 is 10, but minus 6 minus 4 is negative 10. When we come to division, 10 divided by 2 is 5, but 2 divided by 10 is 1/5. So you can see that they are not, the left hand is not equal to the right hand. Then we have the associative property. So with the associative property, that one too, I think you have discussed it. The emphasis is on one operation, 3 integers being operated on. So we have 3 integers, and then we have one operation that is connecting the 3 integers. But it is said that 2 of the integers are being added. One of the integers is being added to the sum of 2 of the integers. So that is where we have, if x, y, and z are integers, then x plus into bracket y plus z bracket close is the same as x plus y, the sum of x plus y plus z. So that is what we have here. And these things are things that you can manage. Then the multiplication too is associative. So x times y times z is the same as if we have x multiplying the product of y and z, it is the same as x multiplying y, and then the product is being multiplied by z. So that is what we have here. Then the distributive property, the example. So we mentioned that the left hand side should be equal to the right hand side, and therefore if we have x times into bracket y plus z, that will be the same as x times y plus x times z. And we gave an example. If we have negative 7 times 3 plus 2, that will be the same as negative 7 times 3 plus negative 7 times 2. You get the same sum, right? You get the same identity. We mentioned 0. The multiplicative identity, we said 1. 0 property, that is 0. Negative property. Any number multiplied by negative number gives you the inverse of that number. So that's what that gives you the negative of that number. So that is what your friend was saying, or gives you the opposite of that number. So any questions so far on the first part? Now we are going to part 2 of the unit 2. We have to go through about 4 before we can finish.
No, please.
Yes. So we are going to discuss the part 2, and that is a continuation of this one. Can we continue to the part 2?
Yes,
Yes,
please.
please.
Yes, please.
So if you look at what we are
So,
discussing, if you look at what we are discussing, they are basic concepts, but you need to revise them. So here in this unit, we would like to describe, we want to visit the description of sets. And here we said that a set is a well-defined, you should all be able to define a set in your own words, but your words should have the ingredients of what is here. That a set is a well-defined collection of distinct objects. You see, the reason why they are saying distinct objects is that you cannot say you have the set 1, 1, 1, comma, 1, comma, that kind of set. How will you name it? You have a set 1, comma, 1, comma, 1, comma, and then 1. What kind of set is that? So that is why they are saying that the set is a well-defined collection of what? Distinct objects. And in our daily lives, we constantly deal with sets, groups of items. Basically, when we talk about set, we talk a group of items. Like the family that we have the nuclear family, we have the extended family. So that can even, then the days of the week, all those ones, days of the week, months of the year, all these ones can constitute a set. So the distinct objects or elements in the set, the distinct objects are referred to as the elements in that given set, or the members of the set. So if you have the set K, like what we have here, K is equal to the element with the set elements, with the elements A, B, C, D, and E. You can see that if we have n number of elements in K, how many do we have?
5.
How many members?
Five elements.
Okay, 5 elements. So all these things. And when you see this sign that you are seeing, if you see this sign, it means belong to this sign, or it's an element of. So, and if it's cross like what you have here, it means that it is not a member of, or it is not an element of. Now, 3 ways to describe sets. We have the listing method, the word description, the set builder notation. So how do we name sets? We can use 3 ways that we can describe our set. We can have the listing method. So V is equal to, then we have listed the elements of the set. You clearly see that these are a set of vowels. Then the word description will be V is equal to vowels of the English alphabet. Then the set builder notation, we have V is equal to X is said that X is a vowel of the English alphabet. So that's perfect, right? Can we move on?
Yes, please.
We are short of about 2 people from the morning lecture. 2 of my people didn't return. So when we come to the listing method, we have examples. Okay, so We have the example as we have given here. We have those that we can complete the elements in the given set, and there are some that are some of the elements are partially listed, but gives us the fair idea about the members in the set. So if you look at the W, the partial list with the pattern, you see we have 0, 1, 2, 3. So whole numbers from 0 up to 100. Whole numbers 0 up to 100. Then if you look at the infinite list, you see that we have 1, 2, 3, 4, 5. So we are talking about natural numbers, set of natural numbers. We didn't limit it, so that those are a set of natural numbers. Then we have the set builder notation, the use of the set builder notation. So we have given an example, but let's look at where we have the first one. You see that X is said that X is a vowel. This one is a basic form, and it gives you a fair idea that lists all the vowels in that set. But we can also restrict the members that will be found in the given set that have been listed using the set builder notation. So W is equal to X is said that X is greater or equal to, X is less or equal to 100, but greater or equal to 0, right? So we have that one. If you want to, that is what the same one that what we had earlier, where we have whole numbers from 0 to 100. This time we are using the set builder notation to tell you that the elements start from 0 and it includes the upper and the lower boundaries or numbers. Then using set membership, we have the set A is equal to X is said that X belongs to natural numbers for the set A, which should correspond with the previous ones. Then we come to the common set theory. Okay, the common set theory symbols. So with this one, the symbols that we use, we have discussed some of them already. We said the first one that you are seeing here, meaning belongs to, or is a member of, or is an element of. Then the next one you are seeing here, meaning it's not a member of, or does not belong to. Then we come to the next one. This one is what? A subset of. Then when we come to this one is union. That's union. Then this intersection. Then we have the null set or the empty set. The misconception lies in where the student has this one, like has introduced the curly bracket as we have here, and ended up putting the null set, the symbol of the null set, into the curly bracket. How do you say it? Is it a null set of a null set?
So it becomes a set of null sets.
But that is a tautology, okay?
I think we can make having one element.
Yeah, so I think it becomes a set of null sets.
It becomes a unit set.
Yeah.
Because the member in that set is what? The member in that set is what?
The null set.
How can the null set? How can the null set be in a set?
Because it's already a set.
When we have already hypothesized that a null set is a subset of any given set. Is that not what we said? I thought we have that hypothesis, right?
Yes.
And so you put in the null set in a curly how do you call it, an empty set again, it doesn't communicate good mathematical thoughts.
Okay.
Yes. So can we say it's a unit set?
No, there's unit set is a set with one member. But here you have a null set and you have put another null set in it. How can you say me that tautology? I don't want to follow it. Go ahead and say that. Yeah.
Okay.
And so that is that. Then we have finite versus infinite set. So for finite sets and infinite set, you understand. A finite set is a set whose first and last member are known. And infinite sets are sets whose last member or some of its members are not known. Hey, how do we say it? Yes. Right? So we have two,
yes,
we can have the members known in the middle, like the second case you are seeing, or we can have the members that are known at the latter part. Once you introduce the 3 dots, it tells you that you are saying, and this tells you the first one, n is equal to natural number. That one, you see clearly that we are talking about positive numbers. But there's integers, we have both positive and negative numbers. So we have the two sides.
So please have
then we have sets, or is a set that contain all other sets, right? Then we have the unit set, which is also known as the and not a set within a set. So take notes. Those of you who saw it and say, hey, is that not what we were talking about? Then we have equivalent sets. So two sets are said to be equivalent when they have what? Right? Equivalent set when they have the same number of elements. Equal set when they have the same element, right?
Yes, sir.
So that is that. Any question, or we'll move to the third one?
So please have a question.
Yeah, ask your question.
So with regards to the infinite sets, from the definition you stated, you said that they are adequate the sequence or their numbers, not all their numbers are known. So in case we have set A with our curly bracket will be 2, 4, 6, 8 with 3 dots within, then we continue to 20. Is that set a finite or infinite
No,
set?
I said a set whose last member are not known, or who
Last member, yeah.
I said whose last member is not
Okay.
known. So you want to give me an example like where we have the 0, 1, 2, 3, and then we bring the 3 dots, and lastly we bring the 100. Is that not what you want to do to me? You think God is a bow-legged person? Okay, so the next one is this one. The next one is the next one has to do with this basic. So this one, 9 slides. Let me see if my TA can occupy you when I'm less busy. Let me see. So, Madam Vivian.
Yes, Doc.
Can you take them through this one? They are just 9 slides.
Yes, Doc.
This basic concept.
Okay,
my
Doc.
teacher. She's my teacher, so you listen to her. will you project or I should be directing it for you? Yeah, because do you have that access?
Yes, please. I can.
You can share, right?
Yes, please.
Okay, then share so that you can manage it at your end.
Okay.
I'm coming to take my off.
Okay. Please, can you see my screen?
Yes, please.
Okay, so section 3, we have power sets and complements. So I'll also give you some few minutes to look for the meaning of subsets and power sets and complements. So you come out with your definition or what subsets, power sets and complements mean. I think we will allow Brother Foster. Am I right, Foster?
Yes.
Please, is the name Foster?
Yeah.
Okay, so you can take us, let your friends research on subsets, power sets, and complements. Then when we come back, we'll come and look through the slides and see what the slide is saying. So we are giving ourselves 3 minutes. 3 minutes. So Foster, you can take over.
I don't think he's around at the moment.
Yeah, I don't think
Okay.
Foster is around.
Is it myself because I'm also called Foster?
We have another Foster.
I think the one that was leading. Okay,
Foster,
any of you
Foster.
can do that.
Foster La.
Yeah, he just left just few seconds ago.
There's a second Foster there if he can take over.
Yeah.
The second Foster, can you lead? Or better still, we can go for a lady, Grace. Grace, can you lead? Where is the deputy cost rep? Where is she? What's her name?
Matilda.
Matt.
Yes. Hello,
Matt.
sir.
Yeah, Matt.
Yes.
Can you lead this session for her?
Oh,
lead this
sorry.
session.
Sir, please. I cannot read from the screen. Oh.
No, we don't ask you to read. Oh. We ask you to go and then read on the subset, power set, and then the complement of set. So it is time for you to brainstorm with your colleagues what they have read, like what Foster was doing this morning.
Oh. Okay. All right.
I didn't ask you to read.
Oh, okay. So colleagues, please, you heard what says. So anyone with any submission or any information on the topic.
Is it the subsets?
The subsets.
So are we talking about subsets?
Yes.
Okay. So
wait.
What we can say about a subset is if you have two given sets, say set A and set B, then if I should get all the elements of set A being found in set B, then I can say or conclude that set A is a subset of set B. Hitherto, when all the elements of a particular set belongs to another set, then we say that set is a subset of the other set. That is subset.
All right. Any other person with other view?
Okay, this is what I also suggest. If every member of, let's say, set A is also a member of set B, then we can say that A is
Please,
said
I
to be
can
a
see the
subset
screen.
of B. Come again.
Hello, who is on the floor?
Foster is speaking.
Please, can you
Okay.
allow Foster to finish, then you come in?
I
Okay,
said,
go on.
if let's say, if every member of, say, set A is also a member of set B, then we can say that set A is said to be a subset of B. And another notation I have about it also, another notion I have about it also is every set is a subset of itself. Thank you.
Please, the last point you made.
The last point I made, I said every set is a subset of itself.
Yeah, can you elaborate it a bit?
Okay. When let's say we have a set, let's say a set A having A, B, and C, having these three elements or members.
Am I the only one who can see the screen? I can't
Come
see my
again.
participants.
I said let's say set A having the element or members A, B, and C. Then if we are asked to find a subset of A, the first subset, as Prof talked about, was empty set. So we have an empty set to be a subset of every set. So we having our empty set, yes, and only A in one set become one set, B in another one become another set, and C also becomes another set. Then A, B in how do you call it, curly bracket becomes another set. AC in curly bracket becomes another set, and BC also becomes another set. Then A, B, and C, because all the members of A, B, and C can also find in the set A, B, and C.
Okay.
That's why I said that every set is a subset of itself.
Please, any other submission from many of you?
Okay. My hand is up. Can I come in?
Oh, yes, please.
Okay. So to add to, we've already explained the notion of a subset. So to add to, when a set is a subset of the other, it doesn't necessarily mean the two sets are equal. Yeah. So for example, if A is having the elements 1, 2, 3, and B is also
Hello.
having the elements.
Hello, sir.
Yeah.
Hello, sir.
Yeah.
Please, can you hold on? I think there's someone having a teaching behind there. Can the person mute the someone is doing teaching? Okay, I think the noise is a bit okay. You can continue, please.
I'll mute them. Don't worry.
All right. So I was saying, in as much as a particular set is a subset of the other, doesn't necessarily mean they are equal. You know, we spoke about equal sets having the same members. So we should have this understanding that if a set is a subset of the other, they are not equal. And I was trying to give an example, as in set A will be having elements 1, 2, 3, and set B will also be having elements 1, 2, 3, 4, 5, and 6. So once the members, that is all the members of set A, belong to the members of set B, we conclude that set A is a subset of set B. However, you realize that set A has only 3 elements and set B has 6 elements, meaning set A is not equal to B, in as much as they are subsets to each other. Thank you. Hello?
The last part is we cannot agree to your last part, much as they are subset to each other. It means this can be found in the other. That's what you are saying.
No, what I mean is one is a subset of the other, rather. That is, set A is a subset of set yes.
But not the other way, right?
Yes, please. Yes, please. Crossword.
Hello, sir.
So I've made my.
Are you taking over?
Matt, are you done?
No.
Yeah.
Matt.
Yes, please. Yes, I'm done.
Please.
I'm asking if you are taking over.
I think we have not done power set. We have not done power set, and we have not done complement.
Okay, so let's move to power.
Yeah, let's
Anyone
talk
with
about
any idea
complement
or
of
information.
Okay, please, my hand is up.
All right, please, you can
Okay,
talk.
so looking at the power set, we are saying that power set refers to the set of all the subsets of a given set.
Can the person please mute the mic, please?
Please come again.
Oh, there's a noise. Somebody's mic is on, and you can hear the feedback from the person's end. Okay, you please go.
What I was saying was, when it comes to the, please come again.
I'm saying continue.
Okay. When it comes to the power set, we are saying that it refers to the set of all the subsets of a given set. So, giving an example, let's say, for instance, we have a set, set A, which is A, which consists of elements A, B, C. Now, when we have the set of 8 subsets, this is set B. You are looking at the subset of set A. So when we have all the subsets of set A, then we put these subsets in another set, giving us, let's say, set K. You can say that subset of B, the set of subsets of set B is the power set of what? Set A. That's what I know. Yeah.
More information or additional information on the subset. Hello.
Okay, Millicent, can we move to the last one, which is the complement of sets? But before we continue, Kojo Brown, please control your mic. I keep muting you. When I do it, then you unmute yourself. I keep doing it. The next thing that you see is that I'll just throw you out of the class. Just like that. So Millicent, take over and let's talk about the last one, which is the complement of.
Hello.
The compliments. I would like to share my understanding. Can I go ahead?
Sure, boss.
Go ahead. I don't know why I can't hear from Millicent again.
Okay.
Millie.
So it's Matilda. It's Matilda rather.
It's Matilda rather. Matt.
Yes.
Okay. Who is on the floor now? We need 2 people. We need 2 people.
Okay, sir.
Foster is here.
Can I come in?
Yeah, you can.
Okay. So when we talk of complement set, I think Foster is not ready. So when you talk of complement set, we are talking about when we have any 2 given sets. Say you have set A with a universal set, then we find out that all the members or elements of contained in set A, all the elements that are not contained in set A can rather be found in the universal set. Then those members becomes the complement of set A. In other words, all the elements that are found in the universal set but not in the set given set, that is set A, becomes the complement of set A.
Okay, I think we've had enough. Matilda. Oh, where are my students? 42.
We are here.
About 8 of your colleagues, they have left. About 8 of your colleagues have left. I
wanted to add up the complement.
I think it's fine. The time is up. Let's continue.
Okay, sir.
Madam Vivian, can you take over?
Please, Madam Vivian's screen is off.
Okay, let me project from here.
So unless you come in, it seems Madam Vivian is not responding.
Yeah, don't worry.
Okay.
I'm going to. I think she's not using the laptop. That's So like you rightly said, okay, these 3 concepts are also very key in sets in dealing with set theories. So the subsets you have, I think you made it clear that if the element of a particular set, if a set can be found in another set, then we say that set is a subset of the other set. But does not mean that the other set is also a subset of. So then we come to the power, so these are the subsets. So A is a subset of B when every element in A is also in B. Then we have proper subsets. So this is where the problem lies in, the proper subsets. So A is a proper subset. If you look at for A is a proper subset of B, if A is a subset of B, but A is not equal to B. So it means that for the subsets, A can be found in B, B can also be found in A. That's what it means. But the proper subsets, they said that is A is a subset of a proper subset of B if all the elements in A can be found in B, but not all the elements in B are in A. I hope that is clear.
Yes, please.
Yes, sir. Yes, please, sir.
Yes, sir. That is the proper subset.
Yes,
And then we have the power set. So the power set is simply the collection, the set of all subsets. Okay, the set of all subsets of a given set is known as what? The power sets. Are you getting it? So those individual sets that your friend formed, after he has the set with the element A, B, and C, he had the unit sets. Then he has the set with the 2 elements. Then he came having the set with the 3 elements, and then he has the NAND set. The set that will contain all this is what we call the power set. Is that okay?
Yes.
Hello, sir.
Please, are you okay?
Yes.
With the power
No, please, sir. How is it different from a special set?
Is the set that contains all the subsets of a given set.
Sir, please, your line is breaking. It is not too clear. We can't hear you.
It's seriously breaking. I can also hear him from my end.
This one is different from a universal.
Prof, please, your line.
Prof, your line keeps breaking.
No.
You have
The line isn't stable. It's breaking.
Probably Prof can't hear us.
Dog. Hello, dog.
But this one is.
Hello, dog. Please, the line is breaking. We can't hear you clear.
Wait. Yes. Yes. 12. Yes. Okay, so let's try and see if you can now hear me well. Can you hear me?
Yes.
Yes.
Exactly.
Yes.
Okay.
You can now hear
Please.
me.
Yeah, it's the network. So I just left the meeting and rejoined. After my TA prompted me that people cannot hear me. Okay, so we were talking about the power sets, and some of your colleagues asked, how is the power set different from the universal set? Is the universal? Let me also ask you this question: is the universal set the same as the power set?
No.
No.
The power set is the set that collects all the subsets of a given set. While the universal set is the mother set of all the subsets.
Yes.
They are not the same. Okay. when we pick the universal set, we said the subsets are obtained from the universal set. The smaller set, they are obtained from the universal set. But if we have a set that collects all the subsets of a given set, we call that set as the power set. I hope that is clear.
Yes, sir.
Yes, sir.
Okay. Titus, your hand is up. Anything for us? So so example is what we have here. This is the example. So look at the power set here. And if you still have some questions, you ask. Please look at these power sets. Go look at this and see if you are okay. So the set is given with the name of the set is K. It has 4 elements. These are the subsets, the individual subsets. But there is a set that contains all the individual subsets. That is what we call the power set. So the P of K is the power set of K. Please, are you okay with it?
Yeah.
Yes,
Yes, sir.
So that this is what we are. And is this the same as the universal set? The one who
No,
has
sir.
that question, look at this and look at the universal. Look at the universal set. Do we write a universal set like this?
No, sir, please.
So that is it. So you simply put it that the power set is the set that contains all the subset of a given set. That is all.
Okay, sir.
Then we come to the properties of power sets. We have the much larger. So the power set is always much larger than the original set. And when we look at the power set that we have for the set K, you realize that the power set of K was much a larger set or has more members than the set K. That one I agree, right?
Yeah.
Yes, sir.
Then we come to countability. The power set of a countable finite set is countable. So once the set in which we drew we come out with the subsets, okay? Once that set is a finite one, then the power set will also automatically be what? A finite one. Is that also true? But if it is infinite, then the power set will also be uncountable. I hope that is true.
Yes, please.
Yes, yes, sir. Yeah.
Then we have the Boolean algebra. That is P of S with the union, intersection, and complement operations form a Boolean algebra structure. So what we are saying here is that the union, intersection, and then the complement operations form a Boolean algebra structure. Please, let's ask AI what a Boolean algebra structure is. Kindly ask. I need somebody who is a prolific, searcher to search that quickly for us. Is somebody there, or I should read mine?
Sir, please, I'm reading.
Good, read.
A Boolean algebra structure is a mathematical structure that captures the logic of true and false, or 1 and 0. It is used in logic, set theory, and digital circuit design.
Okay. Any other? Any other?
To be a Boolean algebra, this must hold true for all A, B, and C belonging to B. Commutative laws. A plus B equals B plus A.
Okay.
And A times B should also be equal to B times A. Then associative laws, distributive laws, identity laws, complement laws.
So that is why those operations or elements were mentioned, that they form the structure of the Boolean sets, the Boolean algebra. What it means that you can perform operations, you can perform the binary operation, you can combine two or more elements, you can also identify the zero elements, you can identify the unit elements, and so forth. But read more on the Boolean algebra. Can we go on?
Yes, please.
Okay. So we come to the complement of a set. And this one too, sometimes people do it like the difference of sets. When I started teaching, I saw some of us. So the complements of set A are elements in the universal set that are not in set A. I hope that is clear.
Yes, sir.
Elements
Yes, sir.
in the universal set that cannot be found in set A are the complements of set A. Do I make that clear to you?
Yes, sir.
Yes,
Or I
sir.
owe you explanation?
Yes.
No.
No.
So here the universal set is given with the elements 0, 1, 2, 3 up to 14. Now the A has the elements 0, 1, 2, 3, 9. So the complement of A, look at it, the elements in universal set which are not in A. Some of you, your phone, today is the first time we are doing it. That's why I'm entertaining you. Akuno. I'm even muting him. It's not possible. Why? Anof. Akuno. Is that not my friend, the one who sat at the back last time?
Nah.
Okay.
That is not a.
Oh, Anof Akono. He should mute himself. His background it produces a lot of. Okay. I was trying to mute him. He particularly, I can't mute him. I don't know why. Okay, so that's fine. So these are examples of complements, and then we come to the difference of sets. Very good. So A difference B or A minus B. Here, if you have A minus B, is the same as elements in A that are not in B. Okay, elements in A that are not in B. That is what it means. A minus B.
Please, sir, is it the same as complement?
No, it's not the same as complement. You see, the complements are there's A complement are elements in the universal set that are not in A. But now you can have two subsets, A and B, and you compare the elements in A and B. Those elements in A that are not in B is what we refer to as A minus B.
Okay.
So take out the B from A. What is left, the element that will be left will be A minus B. Is that okay?
Okay, so a hand is up.
Yeah, let's go.
Okay, so let's take, for instance, you have been given two sets. Let's say set A and then set B, of which there were no clear definition for the universal set. And you are asked to find the complement of B over A. How are you going to go back?
The complement of what?
B over A.
No. That is not complement. That's difference. Difference. A slash B is complement. It's a how do you call it? Difference.
So if that's the case, then it means for the complement there should be a universal set.
How can you find a complement set when there's no universal set? So complement cannot exist if no universal set is identified.
Okay.
Is that clear?
Yes, please.
You can find two sets that have not been related to any universal set, and you can be asked to find A minus B or B minus A.
Good. Good.
Please,
That's
these
what I
things will
wanted.
come in your quizzes. It will come in your quiz and the exams. So take note of them. Don't mix them. Get them right, okay?
Okay.
So these are some of the complements.
Sir, please, can I come in here? So if it is A minus B, sir, if it
let me give you an example. Let me give you an example. Okay. So we have the set A with the element 1, 2, 3. Then we have the set B 1, 2. With the element 1, 2. Now A minus B or with the B is equal to 3 because they are the elements in set A which are not in B. So that is A minus B is equal to the set with the element 3. Are you following?
Yes, please.
The one who asked the question.
So it's clear. Let's continue.
So, sir, in this case, if we are asked to find B minus A.
Okay.
The difference,
if we are
B
to
minus
find B minus, it will be B minus A will be.
It could be an empty set.
Empty set, right?
Yeah, now set.
And
what the B minus A? B that are not in A.
So now,
do you have any elements like that?
No.
You
now
have 1. Two in.
Yeah.
Yes, very noted. Yes, sir.
Yes, please.
Please, I'm a little bit confused.
Don't be.
Yeah, that word there, that word is not academic.
Okay.
Oh, say that. Oh, sir, I need clarification on this. You see,
all right.
Where you are going, I'm not cursing you. But when you are using these words, when I meet you face to face, I'll tell you something. When you are using these words, they are not very good academic words that expressions should be using. Say that, oh, you need clarification on this. Then I know that you are not clear. What is the difference between I'm not clear and then I'm confused? When you say you are confused, it's too wild. Okay?
Okay.
And don't be using those words.
Okay. Okay. Thank you, sir. Thank you. Please, sir, concerning A minus B. Yeah. So in this case, what will be the answer for A minus B?
A minus B.
Yes. But the first example you cited.
Yes, I said A minus B will be the unit set with the element 3. So A minus B is equal to the set with the element 3. Because that is the elements in B that are not, that is the elements in A that is not in B.
Okay.
So A minus B simply means elements in A that are not in B. Now, B minus A means elements in B that are not in A.
Okay. Thank you, sir. Thank you.
The second question your friend asked, where he said, then what about B minus A? If you write equal to 0, it's wrong. You can't write 0. Are you getting it? You can't write 0 for that. If you write 0, it means you are saying that you can't write 0. 0 is an element. So B minus A will be an asset. Is that okay?
Yes, sir.
In other words, you are saying that, oh, sir, there is no element in B that cannot be found in A. Simple. That is what it means. Are you getting it?
Yes, sir.
Yes, sir.
Yes, please.
So then there's so let's look at the De Morgan's law of complement of sets. So A union B all complement is the same as A complement intersection B complement. So you can take any two sets. First, identify the universal sets. And maybe in this case, we have 1, 2, 3, 4. Okay. And if we have the universal set, somebody's mic is making noise like, oh, I can't go. So we want to look at these two laws, the Morgan's law of complement of sets. So we are picking the universal set as the set with the element 1, 2, 3 up to 4. Then our A remains 1, 2, 3. The element 1, 2, 3. Now the B remains 1, 2. Okay. A complement. What should be A complement? A complement is what? 4. B complement is what? 2, 3, 3, 4, right? B complement 3, 4. I'm not too sure if you are following or I'm just doing.
The slide is not coming on.
What is not coming?
The slide.
Oh, can't you see the slide?
We can
what
see
I'm doing, I'm doing it on paper. No. I'm doing it on paper. What I'm saying it on paper.
Okay.
I'm working. I'm doing it on paper.
Okay.
So, Doc, what are the elements of B?
The elements, the universal set has the element 1, 2, 3, 4. The A has the element 1, 2, 3. The B has the element 1, 2. The B, it has the element 1, 2. So now find A complement and find B complement. A complement is 4. B complement is what? 3 and 4, right?
3 and 4.
Yes.
Now let's apply the De Morgan's law. Let's find A union B.
It works.
All complements.
It's 4.
So A union B, all complements. So first we must find A union B. A union B will be what? 1, 2, 3, 4.
1, 2, 3.
A union B will be 1, 2, 3, right?
Yes.
Yes.
So the complements A union B, all complements will be what? 4. Is that not it?
4.
Yes.
Now let's find A complement intersection B complement and see if you get 4.
4. Yes.
So that is the De Morgan's law of complement of sets. Then you can try the second law, which says that A intersection B, all complements is equal to A complement union B complement. Try that one too with the same example. I'm waiting for you. Try. If you get the same thing, let me know.
Please, that also works.
Okay. So these are the two laws of from De Morgan for complement of sets. Okay. Let's go and pick the next piece and discuss that one too. We have 2 more to go. These things, they are not difficult, they are not challenging topic concepts, but you need to pay attention to them, okay?
Yes, please.
Okay, so we are making progress, isn't it?
Yes, sir.
Yes, sir.
Yes, sir.
Okay. So some of my students have gone, but Abigail is here. I am just interested in the ladies. Abigail is here. Coswell, take note. Abigail is here. Those of you using your husband's phones, if I don't mention your name, it means you are not noted here. Abigail is here.
Yes.
And Cecilia is here. Elizabeth is here. Erica is a lady. Yes, Erica is here. Eunice is here.
Kojo too is there.
Is Kojo a female?
Somebody was using
Kojo.
Grace is here.
I know Kojo female.
Grace is here. Then Regina is here. Ramatu. For the ladies, it looks like they are here. The ladies are, most of them are here. So it's the guys who have decided to run away. Can you see the slides?
Let's
If you can see the slide, then let's discuss this one quickly. This one, how many slides do we have? The slide number, I cannot. This one will finish right now. It's 10. This one is 10, so it's more than the previous one, but we'll summarize it right now. Oh, this intersection and union of sets. You know them, isn't it?
Yes, please. Yes, please.
So if you have the set, so if you have the set with the elements, the set A with the element 1, 2, 3 up to 6, and the set B with the element 2, 4, please, it's on the screen. You can see. Can you see?
Yes, please.
Yes, please. Confirm A intersection B. Please confirm A intersection B for me.
It's correct.
4, 6. It's correct.
And so that this one we hurry up and close. Then example 2, prime numbers less than 30, intersection odd numbers less than 37. Do that one too and confirm.
It's correct, sir.
Are you sure it's correct?
Yeah. No, prime number 2 is missing.
That is correct. The other one has odd numbers and 2 is not an odd number.
2 is not an odd number.
Listen to your friend. 2 is missing. 2 is missing. 2 is missing.
Prime number is greater than 30.
So is it correct? Confirm. Can we move on?
It's correct, sir.
It's correct.
Let's move on.
And we come to disjoint sets. When two sets have no element, that's when we said when two sets have no element in common, we said that the two sets are disjoint, right? So this one too. And we have union of sets. For union of sets, we have just done an example. So if we have the set A and B, that set that connects all the elements in A and B is what we refer to as the union of set A and B. A union B. Now, let's look at this property, the properties of union and intersection. So we have the commutative A union B is the same as B union A, and A intersection B is also the same as B intersection A. Do you agree?
Yes, sir.
Is intersection and union commutative?
Yes, please.
Yeah.
Yes, please.
Then associative A union B or union C, will it be the same as A union or union B union C?
Yes, please.
Don't be saying yes sir, yes sir. Let's look at this one. The intersection part, A intersection B or intersection C, will it be the same as B intersection C or intersection A?
Yes, sir. Yes, sir.
Then let's look at the distributive. So the distributive, we have mentioned that union and so we have this is the union one. So we have A union into bracket B intersection C is equal to A union B intersection A union C. Then when we come to intersection, B distributive over union, that's why we have for this one it works. Intersection and union, we can distribute one over the other and you get the same distance. So intersection B union A intersection C. Now let's verify the properties. Our focus will be on the union. How do you call it? Where we have the distributive property. So please confirm. Let's see the first one. Intersection Q union R. So you can see what we have there. Union. And now let's look at intersection R. Do we get the same results?
Yes, please.
Okay. Okay. Then let's look at getting by intersection. P union 2. We are getting 1, 2, 3, 4. Do you get the same thing?
Yes, please.
The one driving a car in my class, that person is doing what? Papa. New Chicano. They want. Say, hey, that your friend, he top it all today. He is the most. He has done it. He has done the best. Hey, why has the papa? Mrs. Say you want to be too in class. You know why? You do all. Your friends are giving you fun. They say you did all. You do all. Okay. Section 5. Please. Properties of operations on set. That's what we are coming to discuss here. Can you see the slides?
Yes, please.
Yes, please.
Yes, we can see. Yes, we can see.
Like I was going to show again. Hey, old age is affecting me. So, the properties of operations on sets. The first one is the commutative property. I think we have explained that. So, yes, we have explained this already. A union B is the same as B union A. And A intersection B is the same as B. We have explained this. So, what is new? Oh, we have explained this one. Master, if you have any question, ask. If you have any question, ask. Otherwise, we'll ask Regina to draw the curtain down. Any question? Can you hear me?
We can hear you.
Yes, please.
Any question? Any question?
Sir, please, sir, it's not a question, but wanted to find out something. You just projected the 3-set problem. Are we going to do it, or we just since you've asked or you wanted to?
This one is only the sessions that have been named. So we don't know whether in our next lesson, which is the unit 3, maybe we are going to start with 3-set problems. Are you getting it? But this one, only the sessions have been named. That's So that is what we have for now.
Okay.
Our materials now ends here. Yes, it ends here. Okay. There's no activity after this one. Or you want to give us one?
Oh, no, not really. I just wanted to.
Okay.
Sir, please, can we have your material?
Yeah, the materials are going to be shared with you right now. Just as I say bye-bye to you, I'm going to share them before I get up from my seat. I'm sitting on a hot seat.
Hot seat,
I tell you, my brother, from morning. Any question? Any question? The
No,
ladies,
sir.
apart from Matilda, I didn't hear your voices. The ladies, any question?
No question, please.
Hello.
Hey, Erica.
Yes.
We just heard your voice.
Oh.
Okay. Okay.
What's up?
The PDF. The PDF. You have made it PDF. Have you converted them to PDF?
You know, that's all. Like this one.
ladies. Oh, the ladies, tell me something, Eric.
We are okay.
Okay, that's fine. Oh, I like that. I like that voice. Yeah, that's nice. Regina, is everything okay?
Yes, please. We are okay.
Good. So I'm going to share the slides right now on your platform. And I've kept you for some time now. I want to release you people.
Thank you, sir.
We will see when we can meet tomorrow.
At dawn.
Yes, if we meet at dawn, it will be nice, Papa. Then you'll be free. You can go to church.
Yes, we are Christians.
Those of who go and
Yeah,
sleep
please,
at
talk about our visitors. So can we have the group link?
No, the link that we are using the same link. The nature of math. You pick the nature of math link. So the course rep will put it on your platform, okay?
Oh, okay. I said some of us we are visitors.
The group link. The group link.
I'm
Okay,
from a
okay.
different center. My class didn't come up. That's why I joined yours.
Oh, but then you are not part of me. So you can't be on my WhatsApp page.
No, I'm saying your slide.
My slides.
Yes, please.
Okay. Okay. All right. So see you all. Bye-bye.
Bye.
Bye.
Bye. God bless you.
Have a nice day.
Please, course rep, I beg you, I place my number on there. So in case drop the slide, kindly help me to have access to it. I beg you. I'm a visitor, very glad from you.
Let me share my number so that you text me instead. Okay.
No problem. I place mine there. So if you have yours, give it to me. I'll pick it right now.
020.
Where's my pen? 020
87
87
11
Come again. 11 or 99.
11
Okay.
375.
375. 0208711
Yes, please.
Your name remains
Emmanuel.
Oh, okay. The year is already written. Thank you.
Hello.
We are from Boga.
Please, if you've not voted, kindly vote on the platform, okay? All right. Goodbye.
First, are you a visitor?
Yes, please.
Hey, then you have like our class like that.
Oh,
next time you pay.
Oh, no problem, my brother. My class didn't come off, and they are saying tomorrow will be by then.
The way you have enjoyed the class, I think you have to pay. Say, Arnold, take something from him.
It's a brother. It's a brother. So brotherly enjoyment.
Yeah, I can see that.
Thank you so much. Right, so okay, now keep on cleaning now.
William, go and continue do your work. We're driving.
Hello, course rep. Hello, course rep. Hello. Hello, course rep.
He's not around.
Hello, Kojo Brown.